So at the end of last class period, we had developed, I think we're talking about small scale fading, right? This phenomenon that happens with antennas where you have an antenna, and unless you're in deep outer space, you're going to have more than one wave striking that antenna due to reflections, scatterings, transmissions, blockages, diffractions, and all the other mechanisms that we experience here on planet Earth. And that means that we call that phenomenon multipath. It's not too hard to figure out why that's the case, because there are multiple paths between any two antennas in a realistic environment because of these propagation mechanisms. And so you get a bunch of waves striking an antenna. That's going to lead to constructive and destructive interference. Waves are oscillating in billions of times per second, but there's going to be a standing wave pattern that if nothing changes in the environment, it's going to give you the exact same amplitude as long as the antenna hangs there. If you start moving, though, you jumble the phases of those multipath components. You jumble them differently depending on which different direction you travel in. And that means that you're going to get basically a random process. Sometimes it's going to be destructive and the signal is going to wiggle upwards. And sometimes it's going to be destructive, kind of wiggle downwards. And we gave a formula on the last class period about Rayleigh fading. So what happens when you have a bunch of multipath, which is very typical in a non-line of sight communications, for example. Rarely do you ever have a direct link to your access point when you're talking on a base station out there somewhere, but you can't see it, so obviously you're blocked. And the radio waves have the exact same problem getting to your phone as if there was a light bulb on the cell tower trying to get your phone. Now, it's not that quite that bad, because at RF, the stuff in our environment is like kind of translucent. It's like dirty glass. You lose some of the light, but you can still make out stuff, radio waves coming in from one side or the other. It would look kind of like a dirty fun house. You ever been to one of those really crappy fairs? I'd like the trailer that they brought in that they unpack and it becomes like a fun house, a house of mirrors. And of course, they didn't do a good job of like cleaning the mirrors. Maybe it's getting the end of the day. Been a lot of people bumping into them and you got smudges all over. That's exactly how it looks like for an RF wave, the environment. A smudgy, grimy fun house. Imagine that. So, we learned about wave interference. We learned that Rayleigh fading results when there's a whole bunch of waves on an end. And you get this constructive-destructive interference phenomenon. We've talked about and worked an example on how to handle that statistically. We said if it's Rayleigh, it's going to follow a Rayleigh distribution in the amplitude, the magnitude of the voltage, or the magnitude of the current coming out of an antenna. Is that if we deal with powers, that's going to be an exponential PDF, probability density function. And if we know the PDF, we can calculate things like how often does this drop below a certain threshold? How often does this rise above a certain threshold? Why would you want that information? Yeah, it could be. I mean, usually you don't worry about overcurrent and saturation for received signal strength because it's just so weak. But remember, a lot of communication systems are due to the performance fails because of signal to interference, not necessarily signal to noise ratio. So we have signal to interference. That means that it is interference limited. There is a man-made transmitter out there in the same frequency that's probably going to disrupt your communications. And that is going to fade. It's also going to experience Rayleigh fading. So your signal may be doing this and you're worried about the noise floor, but there's an interfering signal that's poking above that noise floor frequently, causing degradation in your desired signal. And so that could be an interesting statistical problem to reword it differently. Just say, well, what's the probability that my signal rises above a certain threshold? Because when I do that, I get so much constructive interference that I might interfere with the neighboring cell using this same frequency. So that's where we left it. We had a simple probability density function that we used to calculate outage and probability of exceedance. I did want to add one more thing to this discussion. And the reason why is that you use it in one of your labs coming up. Oh, yeah, there it is. Oh, it's so beautiful. We said that the whole reason we can use our statistical trick for Rayleigh distributions and exponential distributions is that we are invoking the law of large numbers, right? We're adding a bunch of stuff together, actually the central limit theorem. We're adding a bunch of stuff together. It's going to be Gaussian, right? So we had a model like this. We said my voltage coming out of the antenna, total voltage, is going to be the sum over I equals 1 to capital N, all the components of some amplitude v sub I. We said each of these waves kind of looks like a plane wave when it strikes the antenna. So it's going to have a constant amplitude. It's going to have kind of a random phase. And so we modeled that by saying exp to the j, big capital phi sub I, some random variable there. This is usually a constant, though, in a local area. That is a region of 10 or 20 wavelengths that I'm wiggling my antenna around. And then I can separate this out. We used this trick that said, okay, I'm going to use Euler's law. I'm going to break this into real and imaginary terms. And I said, I'm going to add up a bunch of stuff. That's going to give me a random variable x. It's a zero mean Gaussian. And I'm going to add this stuff up. That's going to give me a random variable y. It's also a zero mean Gaussian with the same standard deviation as this. And I had that dart throwing experiment. Remember, I said, this is I, this is Q. If I throw darts and I just start peppering this place with different experiments by throwing darts, and I have a very precise aim that's not very accurate, right? I'm right there on the bullseye, but it's a normal distribution, and x and y happens to be identical. Then the magnitude displacement, which is really what the envelope is Rayleigh distributed. X and y are Gaussian. The magnitude is Rayleigh. So, it's a good question to ask. In what instance would I break the central limit theorem? What condition must hold in this summation for me to actually apply the central limit theorem? Don't answer all at once. You really need to learn to take turns. Well, the rule is got to add a bunch of random variables together to get a Gaussian, right? It doesn't even matter what those distributions are as long as there are a bunch of them. And by a bunch, we mean that no single random variable that I add into the mix contributes a dominant amount of amplitude, or in the case of what we're talking about, power. As soon as I get a really big wave in this distribution, I can break the central limit theorem. So what I mean is, let's say that I had a bunch of little waves, as I always do in multipath propagation, but there was one big wave. So if V1 contains more power than the sum of the remaining components, I'm going to write that expression like this because V squared is proportional to power. If this condition holds, then I start to break the central limit theorem. What does that look like for this problem? Okay. I'm going to find an eraser. Well, I'm going to massage this into a slightly different form. One thing I'm going to do, I'm going to factor this phase, this complex exponential phase term out of the expression. So what I have here is the magnitude xb to the j of 1 times the magnitude of the rest of this, which is this factored out. So I'm going to have V1, which is a constant, plus the sum of I equals 2 to n v sub I dxb to the j. I'm going to call this phi I prime, where phi sub I prime is equal to phi sub I minus phi sub 1. So I'm studying the envelope, the statistics of the envelope of this process. I have a big component out here. I'm just going to take the phase term out, factor that out, and of course everybody at home and in the audience immediately recognize that this is just 1. I can do that without changing, I can factor out a phase without changing the amplitude. And what I'm left with is a constant plus a bunch of complex waves. And does everybody agree that if I study the envelope statistics of this problem, it will be identical to the original problem, which I put in here, which was a randomly phased big term? Okay, so the reason I did that is because now my little dart throwing experiment a bit changed. Now I am a very inaccurate dart thrower. I've got a real value plus what is probably best measured model as a bunch of real valued components plus a bunch of imaginary components. X and Y are still, if the remaining waves satisfy the central limit theorem, then you add them together and they all make Gaussians in real and Gaussians in X, just like the Rayleigh fading. So I really have Rayleigh fading, Gaussian X, Gaussian Y, identically distributed zero mean, plus a constant. So it's almost like I shifted my dart throwing experiment over by the amount V sub 1. And I stand back here and I start throwing my darts. And again, I have a Gaussian here. This time I've got a Gaussian with a mean 1. I get a bunch of points. But I'm still worried about the amplitude, those points, the distance from those points to the origin, because that's going to tell me my signal power. If I sketch that out, it's probably going to look something like this. It doesn't exactly look like a Gaussian, and in fact, it can't be a Gaussian because it's got to go to 0 here. I'll peak somewhere in here. But without knowing anything about the mathematical structure of this PDF, do you suspect this fades worse or better than the Rayleigh case? In other words, do you spend more time closer to 0 in those really deep fades, or do you spend less time than the Rayleigh case? Take a wild guess. Fade worse? No. But I appreciate you tried. Yeah, this should fade less worse, better. Fade better. This should not fade as deeply. Because if you think about it, the farther I put the mean from the origin, the less fading I should see. If I get it in the limit of really, really far away, I should always be hanging around this point, and the distance from there to the origin is going to be about the same envelope. So that's the case where I take my antenna, and I move it around, and I see a little ripple riding on top, but the amplitude seems to be constant. That is a special name. That's called Rician fading. And it's generally accepted that this happens a lot in line of sight environments. So whenever you can see your transmitter, that guy, if you're on your phone right now, tablet, you're surfing the internet, you're probably experiencing Rician fading in this room. Right there, you can see it. Jeremy?
So the V1 in this case would effectively be like the.
Well, you don't want to think of it as an antenna pattern. There is an antenna pattern, of course, being radiated from any transmitter in this room. But you can think of it as the primary frisk path in most instances. You can technically get Rician fading when you don't have a line of sight. But I'll explain why that's a little bit different, and it's not usually nearly like the line of sight case. So it is kind of like the main lobe in the sense that if you've steered the main lobe of your antenna to bore sight so that you can see the physical, like in a point-to-point link, for example, then that's in the main lobe, and that corresponds to the path that's contributing the dominant voltage at your antenna terminal. Recognizing that if there are pathways, multi-path waves that go off bore sight, could be in a side lobe or something, could be just away from, in the main pattern, but away from the peak gain. Or it could be one of these side lobes that you've probably seen already on some of the antennas that we've talked about in class or in your homeworks. And in that case, those are also going to be attenuated because they're off the main direction of the antenna. Okay. Now, let me give you the mathematical formula for Rician fading. It has a special function in it. I don't want you to scare you, and you're not going to have to do anything to really calculate it, although there is a point where you'll need this for your laboratory experiment. So the nice thing, you make a little chart in your notes. That is very helpful. All these different types of fading distributions have a name. And there are dozens and dozens of fading distributions. Some researchers spend their whole careers playing around with fading distributions and do wonderful work that way, characterizing the physical phenomenon around. But you can really get lost in these things and spend way too much time. The two that you need to be familiar with are the Rayleigh fading Where does this occur? Non-line of sight. Typically UHF and above in frequency. And then Rician, which is line of sight. We said here that what do you need to know to characterize a Rayleigh fading distribution? Let's put a column that says need to know. All you need to know, there was only one parameter in that distribution. What was it? average power. If you knew what the average power was, the received area, solve for the standard deviations of those Gaussian sigma. Remember that the envelope PDF was as a function of sigma, and the exponential PDF was a function of the average power, but they're related, of course. Average power, think of this as square root of 2 sigma is RMS voltage or something like that, depending on how the hardware of your antenna and your receiver system. For the Rician, you need to know average power, and then also something called the K factor, which is the ratio of specular power to diffuse. Specular power is the dominant component, the power of that dominant wave striking your antenna. Diffuse power is the sum of all the other stuff. This stuff, that's diffuse power. And so you can even write that in terms of the voltages. V1 squared, if V1 squared is your dominant component, that's going to be the sum of I equals 2 to n over the remaining squared components, because voltage squared is always proportional to power. So K can be any value that you want, right? You can experience a K of 0, which means the dominant component is really, really small compared to the uncountable components of diffuse power, which in K means really what is the special case of K equal to 0? What kind of fading does that become? What's the only kind of other fading you know? Rayleigh, that's right. That means that there is no dominant component when K is equal to 0 and you get a Rayleigh distribution. When K is big, like 10 dB, sometimes they take 10 log base 10 of this and put it in dB. When 10 is 10 dB or a factor of 10, then you start to see a really significant change in the probability density function. For those of you who are interested or are taking the lab, let me give you this formula or the PDF. Everybody can see that at home. Am I getting close to the edge? Okay, close. So here, we said that this was 1 over sigma squared, rho on it, exp to the minus rho squared over 2 sigma squared, and I need a unit step function. And I clamp the values. There are no negative envelopes. For the Rician distribution, this actually does have a closed form. Looks similar to the Rayleigh distribution. But it's a little more complicated. It's got a function called capital I sub 0. If anybody wants to impress me beyond reason, they will tell me, what is the name I sub 0? What kind of special function is that? Yeah. Close. If you take an advanced math course, you'll learn special functions, and you'll probably cover this one the week before you do elliptic integrals. Yes? I don't know if that function shows up in Lambertian scattering problems, but it might. The function that shows up a lot in any problem that has radial symmetry. I will give you a hint. Has anyone seen this function before? Has anyone seen that alphabetical letter before? Let's pretend this is my 4-year-old I'm dealing with. No, I don't blame you for not knowing these functions. I had a professor once, my EMAG professor, in fact, back at Virginia Tech. And I was actually taking a stochastics class from him at the time. And he had this function up there as he was in the middle of deriving something. And he was deriving something, and he said, and clearly this is evaluates to the modified Bessel function of the 0th order. And he just kept blasting on like we were all supposed to know that. And all the rest of us were just looking around like, what did he just do? So it's all, you probably may, I don't know, 50-50 if you ever see this again in your lifetime. But a modified Bessel function is, it solves a differential equation very much like a Bessel function does, with just a slight sign change. So this is, how many of you have seen a Bessel function before? Just one person. No chats claiming in on the there. But if you've taken, did any of you take 4350? How many of you take 4350? Raise your hands. What? Oh, yeah. Have you gotten the waveguide unit yet? Okay, if you do circular waveguides, and I think when I teach it, we usually do circular waveguides at the end of the week, you're going to see J, because it's just, waveguides are circularly cylindrical, they have circular symmetry, you solve a differential equation that makes this J function pop out. So most of these special functions, it's just a matter of getting used to them. You use crazy functions all the time called sine, cosine, and exp. And it turns out that those transcendental functions are really the solutions to differential equations, right? And you can't calculate them in your head. There's not some cute polynomial, finite polynomial way to do it. They're crazy transcendentals. You need infinite series. But eventually you become so comfortable with them that you use them left and right without problem. Advanced mathematicians kind of feel the same way about this function, and also to a lesser extent about that function. And in many ways, they serve as a very similar function to exp and sines and cosines. Like you learned that if you have this differential equation, what's the solution of that differential equation? What'd you say? An exponential, yeah. Well, let's see. It should be, it depends on what the sign is. I think in this case, we could say y equals cosine some constant x. Derivative of cosine is negative sine, derivative of sine, negative sine is negative cosine. And so as long as is the square root of k, I think that solves the differential equation. Now, you're right, it would be an exponential if I flip the sign. And guess what? It's the same deal with the Bessel function and the modified Bessel function. J solves a slightly more complicated differential equation. I don't even know if I have it in my notes here. Oh, here it is. So here's the defining differential equation for the Bessel function. I'm not going to make you compute all this stuff on tests, but it's good to know because you may see it again, especially J, in another class. The Bessel function J is the solution to this equation. So it's a second order differential equation. You see, it's only slightly more complicated than the sine and cosine differential equation. And guess what? If you change the sign here, instead of a J, you get an I. And they even kind of look similar to sines and cosines. Here, let me show you this. Oh, there's my eraser. This part of the table. J sub 0 is oscillatory, just like a sine. In fact, it looks a little bit like a sinc function. You've seen it before. You've seen something that looks kind of like a sinc function. The only one key difference is that the zero crossings are aperiodic, not like a sinc function where every so many intervals it crosses zero. But that kind of looks like that's the solution of this equation. It's oscillatory, and then it dies out at plus or minus infinity. X goes to plus or minus infinity. And I does the exact opposite. It blows up at x equals to infinity. So what this does, this term here kind of blows up the exponential. Normally, Rayleigh fading would look like this with a tail. By multiplying by that thing, you kind of blow it up. Move the peak out of the distribution. But, that said, don't get intimidated if you see these in some of your other classes in the waveguide theory, or if you take a graduate class, or might show up in fiber optics if you take that class. Or, they might even talk about this in the wireless communications class. Anybody in the 4,000 level wireless comms class? Anyway, so that's what I sub 0 is. This thing, the subscript 0, 0 is called the order of the Bessel function. Technically, this is depending on whether you have a plus or a minus here, you get I or J, J or I, but a plus or minus n is the order. So really, this is a family of differential equations. By changing the order, you change a little bit. You have higher order Bessel functions. But my guess is that the ones you will see, you will probably see J0 the most, and the modified Bessel function the second most. And a few of you very lucky nerds later in life may run across higher order Bessel functions if you are lucky. Jeremy.
That's very nice.
Yeah, did I erase that? Oh, yeah. Oh, yeah. Anyway, that's all you need to know. That's all you need to know for this. If you're doing the lab, you'll need to know the terminology. And I think I have you calculate some K factors and do a little bit of parameter fitting. You have to take two antennas, hook them to your spec network analyzer with long cables, and take one and move it around, make an S21 measurement, turn one antenna into a transmitter, the other into the receiver, dial in a narrowband signal, slow down the sweep speed so that you can actually see the fading in the room 365 of bandwidth.